Hi, and welcome to the Section 3.8 video lecture. This is the last video lecture for Chapter 3, and so what we're going to look at is we're going to look at a really important application of implicit differentiation as it applies to what are called related rates. So you can take out your handouts or just some paper to follow along and take notes as we start working on this. We're on page 43 in the Chapter 3 note sheets, which can be found along with all the other video lectures either under this week in Blackboard or on my math lab under handouts, depending on the format of your course. So related rate problem strategy. So suppose we are pumping air into a spherical balloon. So both the volume and the radius of the balloon are increasing over time. If V is the volume and R is the radius of the balloon at an instant of time, then V equals 4/3 pi r cubed. This is just the volume formula for a sphere. Using the chain rule, we can differentiate both sides with respect to time to find an equation relating the rates of V and R with respect to time. Okay, so if we do that, right, what we're going to do is we can use the chain rule, and we can do the derivative of V with respect to R times the derivative of R with respect to T. Okay, so basically what we're going to do is we're just going to do what we did with implicit differentiation, or in this case, we're going to take the derivative of V with respect to R, which in this case would be 4/3 pi times 3 r to the second times the derivative of R with respect to T. Okay, and then we can simplify. So this would be 4 pi r squared dr dt. So if we know the radius of the balloon and the volume, the rate at which the volume is increasing at a given instant in time, then we can solve the equation for the rate at which the radius is changing to find out how fast the radius is increasing at that instant. Note that it is easier to directly measure the rate of increase of the values, the rate at which air is being pumped into the balloon. So you could have a regulator on the machine you're using to pump up the balloon that could tell you how fast the volume of the balloon is increasing. And so then we'd be able to figure out how fast the rate is increasing. So that's going to be the idea here. So what we're going to do now is just look at a bunch of different practice problems that go along with this idea. So suppose a cube surface area increases at a rate of 72 inches cubed a second. At what rate is the cube's volume changing when the edge length is x equals 3 inches? Okay, so the first thing you want to look for in this problem is just write down as much information as you can. You're going to want some sort of formula that relates the variables in your problem. So in this case, we're looking at surface area and we're looking at volume, okay? And we're going to have an edge length. So what we have going on here, and it could be helpful to draw pictures, we've got a cube where the edge length is changing. So let's call that x. And so since we're talking about volume and surface area, it's probably going to be useful to have formulas for both. Okay. So we've got the formula for volume of a cube is just x cubed, right? Length times width times height. And the volume for surface area is you simply add together the areas of each side. So let's call that surface area. So the area of each side is x times x, and there's 6 sides to a cube, so that would be 6x squared. Now, other things we know in this problem is we know we want to deal with this, that the surface area increases at a rate of 72 inches squared per second. Well, one of the things we know is that rates are derivatives. So one way to write this 72 inches squared per second using variables would be the derivative of the surface area divided by in terms of time. And that's going to be 72 inches squared per second. And then the other thing we know is that x, we want to do this when x equals 3. And the last thing we know is we're looking for the rate at which the volume is changing. So dv dt is our unknown, the thing we're looking for. So now the question is, we've got these two great formulas. How do we get ds a over dt and dv over dt into this problem? Well, the way you do that is by taking the derivatives of both these formulas with respect to time. So we've got dd of v equal, take the derivative with respect to time of both sides of the formula on the left and the formula on the right. Okay, so the derivative of volume with respect to time is simply dv dt. We don't actually have any way to know what value that is. In fact, that's what we're looking for. To do this derivative on the right, we use implicit differentiation. So that's going to be 3x squared dx dt. Okay, over here we get dsa dt equals, do the implicit differentiation. So not 18, sorry, 12. The derivative of 6x squared is 12x, and then we are taking the derivative of x with respect to t, so we get dx dt. Okay, so we have 3 unknowns in the formula we're solving for because we want to solve for dv dt. And so the way, one question we can ask, is there a way to get that down to one unknown where we know the value of it? In this case, we know x, so how can I get rid of this dx dt? Well, I can use this formula over here because I know that dsa dt is 72. And so we can solve for dx dt. So divide both sides by 12x. Right, and you get 72 divided by 12 is 6, so 6 over x equals dx dt. And so now we can substitute that in for dx dt. So dv dt equals 3x squared times 6 over x. Cancel an x, and you get dv dt equals 18x. And now we can just plug in the 3. So dv dt equals 18 times 3, which is 54 inches cubed per second. Okay, and so that's the idea. So when you're doing related range problems, you're looking for formulas that involve the variables you're dealing with. You're going to take the derivative of those with respect to time to get these rates into the problem. And then from there, it should mostly just be algebra to solve for the variable you're looking for. So we can practice doing more of this implicit differentiation with these rates. And then after we do that, we'll get into more application problems. So the power in watts, the P of an electric circuit is related to the circuit's resistance R in ohms and the current I in amps by the equation P equals Ri squared. How are dB over dt, dr over dt, and di over dt related if none of P, R, and I are constant? Well, all that's asking us to do is take this formula and take the derivative of both sides to find these derivatives, right? So the derivative of P with respect to T is just dP over dt. And then on the right-hand side, I have to do the product rule. So this is the first thing times the derivative of the second thing plus the derivative of the first thing times the second thing. So dP over dt equals the derivative of I squared is 2I di dt, and the derivative of R is dr dt times I squared. So dP dt equals 2IR di dt plus I squared dr dt. And then you could solve for any of those formulas as you want. Okay. Now, one of the interesting things that happens with these is, well, what if one of them is a constant? So if I look down here, how is dr over dt related to di over dt if P is constant? Well, what happens when a, what is the derivative of a constant? Well, we talked about this before. The derivative of a constant is 0. So to do this part, we just let, if P is constant, then dP dt is 0. So I could just use this formula I already have, and we get 0 equals 2I r di dt plus I squared dr dt. And then we just want to solve for dr dt because we want to say how is dr dt related to di dt. So solve for that. So subtract 2 IR di dt from both sides. Okay, and then divide by I squared. So we're going to get dr dt equals negative 2IR over I squared di dt, and then we can simplify that a little bit. Dr dt equals negative 2R over I di dt. Okay, so the rate at which the ohms change is equal to negative 2 times the number of ohms over the number of amps times the rate at which the amps is changing, assuming that the power is constant in this circuit. Okay, so that's the idea. So why don't you guys at this point pause this video and see if you can do these other ones here at the bottom, and then start the video when you're ready. Okay, so how is dV dt related to dH dt if R is constant? So we take the derivative of both sides. And then we do this derivative. Now, if R is constant, that means this whole thing is a constant multiple. How do we do derivatives with constant multiples? We just bring them out in front. So that means when we go to do this, on the left-hand side, we get dV over dt. We bring the constant multiple out in front, which is 1/3 pi r squared. And then we do derivative of h with respect to t, which is dH dt. And that's it. Okay? Similarly, if I want to do the same thing, but I want to let h be constant, and I want to look for dr, we do the same thing. But in this case, the constant multiple is 1/3 pi r h, and then I need to do the derivative of r squared. So there's going to be slightly more work here. So the constant multiple is 1/3 pi h, and then we do the derivative of r squared with respect to t, which is 2r dr dt. And so dV dt ends up being 2/3 pi rh dr dt. Okay, and then if neither of them are constant, then we're going to have to use the product rule. So we set it up the same way that we've done the other two. But now there are no constant multiples, so these two things are being multiplied together, so I need to treat them as such. So I need to use the product rule. So we do dV dt equals the first thing, so 1/3 pi r squared, times the derivative of the second thing, plus the derivative of the first thing times the second thing. Okay? So the derivative of h is, with respect to t, is just dH dt, and the derivative of 1/3 pi r squared is just 2/3 pi r h dr dt. So notice we got the two pieces that we got up here, and if it turned out that one of them is let's go back. If I had done this problem here first, I could have used the same rule I used up here, which is that if a variable is constant, then its derivative is 0. So if h is constant, then this part is 0, which means 0 times anything is 0, so that would just go away, and so we'd get this answer. Notice how those are the same. And the same thing happens if we let r be 0. Then this whole part cancels out, and we just get the first part. Okay, so that's how those things are all related. So that's just more practice with this idea of implicit differentiation and constant multiples. Okay, so now that we've looked at how implicit differentiation, along with this idea of, can be used to solve for certain rates. Let's go ahead and put kind of all this together and start looking at some more complicated word problems that go along with this idea. So here are some steps you can use to follow. They're great. I'm just going to kind of run through how to do some problems that'll basically be using these steps. So here's an example. So two commercial airplanes are flying at an altitude of 40,000 feet along a straight line courses that intersect at right angles. Plane A is approaching the intersection point at a speed of 442 knots, which is just shorthand for nautical miles per hour, and nautical mile is 2,000 yards. Plane B is approaching the intersection at 481 knots. At what rate is the distance between the planes changing when A is 5 nautical miles from the intersection point and B is 12 nautical miles from the intersection point? Okay, so the idea here is we can draw a picture. Here's plane A, here's plane B. They're on an intersection course, so they're going to run through the same point, and they're at the same altitude, so that means we can think of this as two-dimensional. That's the only reason they tell you that their altitudes here is so that you're only looking at this in 2 dimensions. Okay, so what you should notice here is that this makes a right triangle. Okay, so how are plane A and plane B related to each other? Well, one of the ways they're related to each other and the speed that they're approaching each other is they're related through their distances, right? So we've got the distance A is from the intersection point. We've got the distance B that plane B is from the intersection point. And then we've also got distance, let's call it C, which is the distance between the two planes. So the question is, this gives us a way that those planes are related to each other. So that's can be our formula. So we got using the Pythagorean Theorem, a squared plus b squared equals c squared. And what they'd like us to do is what rate is the distance between the planes changing when A is 5 nautical miles from the intersection point and B is 12 nautical miles from the intersection point. Well, we want to get rates into this. Well, the way you get rates into any problem, right, is to do the derivative. So if I take the derivative of both sides, that will bring it, with respect to time, that will bring in these rates. So if we do those, the derivative of a squared with respect to t is 2a dA dt. The derivative of b squared is 2b dB dt. And the rate c is, the derivative c with respect to t is is 2c dc dt. Okay? And now we can start substituting some things in here, right? We know most of these. What we want to know is we want to know the rate the distance between the planes is changing. Well, that is this variable right here, dc dt. So that's what we're going to be solving for. And if, in fact, if you wanted to, you could go ahead and solve for it by dividing both sides by 2c. So I'm going to write this in a slightly different order, but we should get dc dt equals 2a dA dt plus 2b dB dt all over 2c. And then if you wanted, you could cancel out all those 2's. And now we just need to start substituting in for some of these. Well, we know A is 5 nautical miles from the point, so that is our A. So let's start plugging in some of these. So that's A is 5. We know the rate at which we're approaching this point. So we know the rate that A is going, right? The rate that the A is changing is it's going down at 442 knots. So that'd be times negative 442. We know that plane B is 12 nautical miles from the intersection. So that's 12. And we know that it's traveling at 480. So that's making the distance B shrink at the rate of 481 knots. And then we actually know how far apart C is, but we just haven't written it out right. If A is 5 and B is 12, then C we can find by simply using the Pythagorean theorem. So the square root of 25 plus 12 squared is 144, so 169 equals C, which is 13. So we can plug that in. And so now we should just be able to plug this formula into our calculator, and it will tell us the rate at which the rate at which the distance between them is changing. So 5 times negative 442 plus 12 times negative 41 divided by 13. So that's negative 614 knots. So they are approaching each other. The distance between them is shrinking by 614 nautical miles per hour. And that's a really good example of how you're going to deal with pretty much all these problems. Is you want to find a formula that involves all the variables, then you're going to take the derivatives to get the rates into the problem, and then you're going to solve for the variable you're looking for, which will be a rate, like it was here, and then we're going to substitute in all the known information. One of the key things here is you don't want to substitute in for the known information until after you've taken the derivative. Okay? So let's look at another example. Oh, and this is the one that I always forget, that I forgot to include the picture. So let's see. Let me go into the book real quick and find the picture for this. Okay, so the problem says that coffee is draining from a canonical, which is just a cone, filter into a cylindrical coffee pot. Okay, and so what that looks like is it looks like this. Okay, we've got a cone, and then we've got below that, we've got a cylinder. Okay, and what we know about both of these is that they have a width of 6 inches, and the cone has a height of 6 inches. Okay, and that's really all we know about it. So coffee is draining. So we've got some coffee in here, and it's dropping into the pot at a rate of 10 inches cubed per minute. Okay, so that means, anyway, so we'll get back to that. How fast is the level in the pot rising when the coffee in the cone is 5 inches deep, and how fast is the level in the cone falling at the same time? Okay, so what we know is, well, what we want to start out with here is similar to the last problem. Is now that we've kind of got the problem set up, what we want to do is we want to get some formulas going on here. So if I want to talk about the level, and I'm talking about amount in a 3D object, that means I'm going to be using volumes. So the formulas that are important here are the volume of a cone, which we'll just use V sub C for that. Actually, let's do it this way. Let's call that Z sub F. So let's use F for the filter. So V sub F is 1/3 pi R squared times H. And let's use subscripts of F on those to say that we're talking about the filter. And then we've got the same thing for the pot. So we've got V sub P is, and then we find the formula for that, which is pi R squared sub P times H sub P. Okay. And what we're looking for is we're looking to figure out how fast these H's are changing. Okay. So those are our formulas. Okay. So there's our formula. So now what we probably want to do here is we want to do a couple things. We need to get rid of some variables and make some things simpler in this problem. So the first thing to notice is the height and the diameter of the cone are the same. And so what that means is that the ratio of the height of the cone, the height of the filter, to the diameter of the filter are equal, and the radius is half the diameter. So H sub F is the same as R sub F over 2. Okay? And so that's changing. So we could also say, the easier way to say that is to say 2H sub F equals R sub F. And so what that allows us to do is allows us to get rid of this variable R sub F. So we're down one less variable because we care about the level, which is the height. Okay, so the volume of F. Okay, so that was just a little side work, which is why I did it in a different color, is equal to 1/3 pi times 2h sub f squared times h sub f. Okay, and if we simplify that, that's v sub f equals 4/3 pi h sub f cubed is the formula for the volume of the filter. Okay, the other thing we know is the pot has a diameter of 3, and unlike the diameter of the filter, which is the level of the pot goes down, the radius gets smaller, which is why we needed to keep it as a variable. Over here, we know the radius of this is always going to be 3. While the height of the pot is changing, the radius is not, because it's a cylinder. So that means I can substitute in 3, which is the radius, for r sub p. And so that gives me a formula for the volume of 9 pi h sub p. Okay, so now we've got ourselves down to more simpler formulas. So what we want to do now is we want to take the derivatives, right? We need to get the rates into the problem, so we'll take the derivative of both sides. So the derivative with respect to t of both sides of both these formulas. Okay, so we get the derivative of the volume with respect to t is equal to, so I do the derivative over here, so 4/3 pi are constants, so I'm just doing the derivative of h of f cubed, so we bring the 3 down, so that'll cancel with this 3, so we end up with 4 pi h of f squared, and then over here, d of h of f over d of t. Sorry, don't forget about, we took the derivative of something with respect to a different variable, so I get that term because we had to use implicit differentiation. And then for the other one, we're going to get 9 pi h of p dt. And I forgot a variable here, so this should be v sub p. Okay, so now there's one other piece of information in this problem we haven't used yet, which is the rate at which the coffee is draining from one to the other. So that would be the rate at which the volume is changing. So the volume in the cone in the filter is going down, and the volume in the pot is going up. So d sub vf dt is -10, and d sub vp dt is +10. So we can substitute those into our formulas, and then we'll almost be done. We'll just need to solve what's left. So this will be -10 equals 4 pi h of f squared dh of f over dt. Okay. And then over here, it's just going to be 10 times 9 pi h of p dt. Okay, and so now for both of these, we just want to solve and then also substitute in. So on the left-hand side, we're going to get -10 over 4 pi. H of f is 5 inches deep, right? So it's 5 inches deep, so we're going to substitute that in here. So 4 pi times 5 squared in for this variable equals dh of f over dt. And then on the other one, we're just going to divide by 9 pi. So this would be 10 over 9 pi equals h of p dt. And then I can just substitute those in our calculator to get the final answers. So the rate at which the height of the filter is changing is -10 divided by 4 pi times 25, which is -0.031 inches per second, per minute. And the rate at which the height of the pod is changing is 10 divided by 9 pi, which is 0.354 inches per minute. Okay, so that's the idea. So there's another example. So that's an example that involves volumes, which is a fairly common type of problem. So there's going to be a lot of geometry ones that involve things like the Pythagorean Theorem, and then there'll be a lot like this where we use volume formulas. Another really common type of problem is one that involves trig functions. So let's look at one like that. So on a morning of a day when the sun will pass directly overhead, the shadow of an 80-foot building at level ground is 60 feet long. At the moment in question, the angle the sun makes with the ground is increasing at a rate of 0.27 degrees per minute. At what rate is the shadow decreasing? Remember to use radians. Express your answer in inches per minute to the nearest tenth. Okay, so what we've got is we've got this building, right? And then we've got the sun. I like to draw my sun happy. That's not obviously not necessary. And then we've got the shadow, okay, along the bottom. And then we've got this angle theta that the sun makes with the ground. Now, the shadow is changing, so we're going to give that the name of a variable. And then the height is constant of the building, but let's just call that B for now. And so what we need a formula that relates theta, S, and B. And the formula that does that is tangent, right? Because the tangent of theta is equal to opposite over hypotenuse, so B over S. Okay? And now what we can do is substitute in the constant, because that never changes, so this will be tangent of theta equals 10 over S. And then what we can do is we can just do some trig. Take the derivative, and then we'll go from there. So if we do the derivative here, so the derivative of tangent is secant squared theta d theta dt, and the derivative of 10 over s with respect to theta would be negative 10 over s squared ds dt. Okay, and so what we need to do is we want to solve for the variable we care about, which is ds dt. So I'm going to multiply both sides by the reciprocal. So I'm going to write it kind of backwards. I'm going to write ds dt first, and then it'll be negative s squared over 10 times secant squared theta d theta dt. Okay, and now all we have to do is substitute in for s and theta and d theta dt, which will take a little bit of work, but we'll be able to manage it. So the first part is d theta dt is given to us here in the problem. So d theta dt is 0.27 degrees per minute. Now, the biggest problem with that is that's not in radians, which they tell us to use. So what you want to do is you want to multiply that to change this into radians. Well, to do that, you've got pi radians in every 180 degrees. So this will end up being d theta dt will be 0.27 pi over 180. Okay. The other thing we need to substitute in are for theta and s squared. Well, s is 60, right? We know the shadow is 60 feet long at the moment we care about, so s is going to be 60. And then the other part is figuring out what theta is. Well, theta, we can use the tangent idea. So tangent of theta equals opposite over adjacent. Well, the building is 80 over 60, so theta equals inverse tangent, and then we can reduce 80 over 60 to 4/3. And now we can just substitute all that information into this formula and plug in our calculator. So this is going to be the rate at which the shadow is changing, is going to be negative 60 squared over 10 times secant squared of inverse tangent of 4/3 times 0.27 pi over 180. And like I said, you could type that all in your calculator exactly like that. Okay, so here, I'll just go ahead and put this one up on the screen. So in your scientific calculator, it's going to be negative 60 squared divided by 10 times going to trig to get the secant of trig, again, to get inverse tangent of 4 divided by 3. Close the first parenthesis, close the second parenthesis, and then square it. Right, we're squaring secant times times 0.27 pi divided by 180. And so we get negative 4.712. Negative 4.712 feet per minute, which seems too big, so I feel like I did something wrong. Oh, they want it in inches per minute. But no, that's going to be... Okay, I found my mistake, and it's a pretty small one in hindsight, but it had a pretty big impact on the answer here. So what I did wrong is I don't know why I put 10 here for B, right here, right, sorry, where I'm erasing. Because what this should be is B, the height of the building. Well, the height of the building is 80. Okay, so where that comes into play is anywhere we add that 10, it should be 80. So I can go through and that's all I really have to do here is erase those 10s. And make them all 80s. Okay, and so now in our calculator, all I have to do is go in and change this 10 right here to an 80, and that should give me the right answer. Yeah, that's a lot better. Negative 0.589. Negative 0.589 feet per minute. Now notice that is not the units they want the answer in. What they want it in is they want it in inches per minute. So what I need to do is another conversion like I did here into radians. I need to convert this into inches. So you just multiply by 12 inches in 1 foot. And that'll cancel out the foot units and leave us with inches. So we're going to multiply by 12 and then round to the nearest tenth. So you can double click on the answer you just got times 12. And so that's negative 7.1 inches per minute. And there's the correct answer. Okay, so that's the idea. So we had a little struggle there, but we figured it out in the end. Okay. So what I'd like y'all to do now is pause the video, and I've just got 2 more examples for you to try on your own. These are both Pythagorean Theorem ones. You'll get practice with other ones in the homework, but go ahead and try these 2 Pythagorean Theorem ones. Then hit play. We'll go through them together, and that'll be it for this section. Okay, so let's go ahead and go through these together. So what we have in this first case is we've got a girl over here, and she's flying a kite. Right, kind of thing. That's not a very good kite. That was a little too much of a diamond. Okay, there's my kite, and she's holding it with a string. The kite is, so what we've got going on here, right, is we've got the length of the string, the distance, horizontal distance from the girl to the kite, which let's call that, if I'm going to use distance, let's call that capital D, and then you've got the height of the kite off the ground. So you should notice this is a right triangle, which means you're probably going to use this formula, right? S squared equals D squared plus H squared. Okay, and so we could go ahead and find the derivative of that, which is the same basic idea as the derivative we used earlier. So that would be, the derivative of this is 2s ds dt equals 2d dd dt plus 2h dh dt. Okay, and in this case, we want to know how fast must she let out the string when the kite is 500 feet from her. So we want to know this variable, ds dt, so divide both sides by 2. And once again, you can cancel out the 2's, similar to what we did before. So now we want to plug in as much information as we can. So the kite is at a height of 300 feet. So that means this h is going to be 300. The wind is carrying the kite horizontally away from her at a rate of 25 meters per second. Well, that's going to be the change in how far away it is. And how fast must she let out the kite string when it's 500 feet from her? Okay. So that's going to be our S. And then we can actually figure out the other things going on here. So let's go ahead and plug in the obvious ones that we know. So we don't know D yet. We know this is 25. We know H is 300. We don't know DH dt yet. We know S is 500. Okay. So because this is a right triangle, I can find D by using the Pythagorean theorem. So 500 squared, well, actually, let's write it this way. 300 squared plus D squared equals 500 squared. And when you solve that for D, you're going to get D equals 400. Okay, so we can plug that in. Okay, and then the only other question is, what about dH dt? Well, what do we know about H? Well, H is constant, right? The height of the kite is always 300 feet. So since H is constant, what is dH dt? What is the derivative of constant? Well, the derivative of constant is 0. So this would be plus 300 times 0 over 500. So ds dt equals 400 times 25 divided by 500, which is 20 feet per second. Okay, so that's pretty similar to the one we already did together. Okay, and then let's just try one more. So let's go through this one. So highway patrol plane flies 3 miles above level. Straight road at a steady 120 miles per hour. The pilot sees an oncoming car with the radar, determines that at the instant the line of sight distance between the plane and the car is 5 miles. The line of sight distance is decreasing at a rate of 160. Find the car's speed along the highway. Okay, so what you've got here is like this. We've got the plane up here and the car on the ground. We've got a line of sight distance, so let's call that H. We've got, L, capital L. We've got the height of the plane, and then we've got the distance between them, which, well, let's just call that B for distance between, I guess. So once again, start out the exact same way. I'm going to write it like this time, but you write out the Pythagorean theorem and then take the derivative, which is 2b dB dt plus 2h dH dt, and then you've got equals 2L dL dt. In this case, we want to know, what is the car's speed? Well, the car's speed is going to be related to how fast the how fast the distance between them is changing, okay, on the horizontal. So we want to solve for that. So you can subtract 2h dh dt from both sides. And then divide by 2b. So db dt, the rate at which the distance between them is changing is going to be 2l. dl dt, well, not 2l. Let's cancel out the 2's. So l dl dt minus h dh dt over 2, not 2, sorry, I canceled out the 2's, over b. Okay, and now we just need to substitute into that formula. So, things we know. We know the line of sight distance is decreasing at 160 miles per hour, and we know the line of sight distance is 5 miles. So L, line of sight, is 5, and dl dt is negative 160. We also know the height of this is 3 miles of the plane, and we know that height is constant, so that means the derivative here is going to be 0. And then we can use the Pythagorean theorem to find b. So it'll be 3 squared plus b squared equals 5 squared. So that's, when you do that, you'll get b equals 4. Okay, so db dt is negative negative 200. Okay, so the distance between the two vehicles is changing at 200 miles per hour, but that's not what they asked for. They asked for the car speed. So if the plane is going 120 this way, and the distance between them is changing at negative 200, then how fast does the car have to be going? And the answer to that is 80 miles per hour. Okay, so that's it for section 3.8, and that's all we're going to cover in chapter 3. So make sure you're doing your homework, and if you have any questions about anything, feel free to reach out to me and we can talk about it.